before we get started, you can find all the slides online on my GitHub. If you go there, you'll be able to click through right to them. If you can't see the screen for whatever reason, you can also find all the source there if you're curious. All right. I am Seth Samuel. I'm here to talk to you about WebAssembly and the future of JavaScript. I've been in New York, Portland, various other places. Portland, back in New York, where I'm working for Airtime right now. I get to work with cool stuff like video and microservices and video microservices and service video micro. No, not the last one. But the first three are fun and cool. Come talk to me if you're interested. We love Node. That's the end of the business talk. All right. One more piece of business, the disclaimer. First, this is a pretty in-the-weeds talk. We're going to get deep and into really weird stuff that's way out there right now. If you get lost, don't feel bad. It's probably my fault, not yours. Come ask me questions. I love answering questions about this. The other thing is, I like to talk and work with things that are right on the bleeding edge of, we can put this in production if we're not dealing with money or health and lives and things like that. This is a little bit past that. You do not want to run this in production yet. If you do, please tell me, because that would be awesome, and I claim no responsibility whatsoever for what happens. Come back next year, and hopefully we'll actually be able to talk about doing this stuff in production. So, what's WebAssembly? Well, first, there's the web. Everyone here probably knows something about the web, but just in case, a brief history. Charles Babbage, Ada Lovelace, Alan Turing, Grace Hopper, Tim Berners-Lee, Brendan Eich, Brian Dahl, you. All right, that's the web. Cool. So next is assembly. This one's going to take a little bit longer to get everybody up to speed. What is assembly? Well, first we have to ask, what are programming languages? Because we work every day with programming languages and maybe don't think about why we have them at all. And the answer is that programming languages are a bridge between human thought and machine processing. And we need this bridge. Why? Well, we want this bridge to look like this. Very nice bridge, it's very sturdy. It's probably not going anywhere, we hope. But a lot of times the bridge looks more like this. And certain languages, we heard Cold Fusion earlier, and I'm totally okay throwing Cold Fusion under the bus because I also had to work with it way back in the day. Looks a lot more like this. So why do we need these abstractions and bridges at all? Well, the answer is that computers are nothing more than electrons. They're just a series of tubes piping electrons across tiny, tiny pieces of metal. And we take these electrons and we pipe them in just the right way that we can do math. And that's crazy and incredible and magical, but it's really hard to program React.js in electrons. So we go one step up and we get machine code, and it looks a lot like that. It's better than electrons. We all are probably a little more familiar with numbers than actually pushing around, subatomic particles. But it's still pretty hard to work with. It's just a bunch of numbers. And so the next step up is assembly. And really, this is the biggest jump in abstraction in this entire series where we'll eventually get to JavaScript and beyond. Because here we've gone from numbers to actual conceptual work. And so what this little snippet of assembly is doing is putting the number 45 in one memory spot. Anyone who knows assembly better than me, please don't shout out that I'm wrong. 55 in another memory spot. It takes those two memory spots, adds them together, and then does something. But the point is that it's taking these addition and multiplication and simple low-level operations and turning them to something more conceptual, where we have this idea of memory and variables and operating on them. And so for the longest time, this was how programming was done, not in this actual assembly, which is, I think, is something x86y, but in this same concept of really low-level operations that were very close to how a computer actually works. So why was Grace Hopper in that very quick overview? Other than she looks awesome in uniform and gives zero fucks about any of us. Yeah. She was one of the pioneers who pushed the idea that we could program computers using languages that were more like our language. That we could do things in a way that was easier for us to think about and then turn that into something that would work for the computer. And so this idea was called a higher order or higher level language. These days we call them lower level languages because we've come a long way. So this is a little bit of C, and the here is important because, like I said, in 1950 whatever, this piece of code would have been super high level and close to human thought and great to work with compared to punch cards that just translated down into math. And so we can see this is pretty low level compared to something like JavaScript. We have concepts of malloc, which if you don't know, actually takes a chunk of computer memory and allocates it for use. Free, which says I'm done with this. A pointer, which is a variable that actually, just like it says, points at a point of memory. And so this is very low level compared to something like JavaScript. But we also have things like types. We have int here, which specifies that this particular variable is going to hold an integer of some size. And in fact, we can see we're calling size of int, which is really great. It means that we can run this code or compile this code on any computer, and it will automatically know how many bytes to allocate to store this int in the memory eventually. And that's a huge step up from assembly, where you have to know all that yourself and keep track of it and do a whole bunch of work to do that. So then we go another step higher, and we got good old JavaScript. This is horrible JavaScript. Please never write any JavaScript like this. But it illustrates the point that all of that memory code, all of those pointers have gone away, and now we're just thinking in terms of variables and data structures. So we allocate a variable s to be 1, and then we assign it to be an array that has the string of hello inside of it. We set the third, indexed by 2, element equal to empire, and then we set a key of the string of a to node. And so we've mixed up all sorts of variables in here. We're not setting ahead of time what the size of these data structures is going to be. And that frees us to work really quickly and really fast and express ideas much closer to how we think. And we can even take it a step further. There are visual programming languages. This is Unity, which gives you this sort of flow chart-like way. I think this is switching a light switch, light on and off when your user, hits a switch. If you've ever worked with Lego Mindstorms, I think that the other game engines have things like this as well. It's very visual, it's very conceptual, and it's taking us even one step above this very accessible code that higher order languages like JavaScript and Ruby and Python give us. So what's the downside? The higher the level you go, the less efficient they are. And there's a big asterisk there. It's like 6 inches high on this screen. It should probably be like this high, because this is a very rough rule of thumb. It does hold true in general. The more abstraction you get, the less efficient your eventual code on the processor is going to be. And we accept that trade-off because it lets us write programs more quickly, more understandably, which means less buggy and easier to maintain. But sometimes you really want that efficiency. And so a few years ago, people wanted that efficiency, and they started working on something called ASM.js. So what ASM.js is a subset of JavaScript that will compile down more efficiently in the browser, specifically Firefox. And it looks a lot like normal JavaScript. Really, the only weird thing up here is this pipe 0 right after the x equals x pipe 0. And what that is there's no types in JavaScript. And one of the biggest overheads in higher order languages that are loosely typed is figuring out the type of the variable when it comes time to run the program. And this is what they came up with, and it was a fairly common, and still is, way of declaring that x is going to be an integer. It basically says 0 out all the parts that aren't an integer. And do the same with y, add them together, and return it. And so this is great. If you're running Mozilla and you if you loaded this piece of JavaScript into your application, then it would run much faster. This one probably not much because it's just adding, but it's comparable type programs would run much faster. But this is pretty clunky. It's a little awkward. There's all this sort of weird boilerplate. JavaScript just wasn't meant to do this sort of thing intentionally. We made that trade-off intentionally for the benefits it gives us. And it doesn't solve all of the problems of the JavaScript ecosystem. And we'll get to the problems we're trying to solve a little later when we get to the solutions. And so what came next was called Webassembly. And what Webassembly really boils down to is an abstract syntax tree, which we already heard about today, which is great because it means I can gloss over it now, that browsers are going to be able to transform really efficiently. So the WebAssembly, the syntax tree, WAST, there's a lot of fun to say acronyms in WebAssembly. The WAST is a shared target for compilers. And what that means is whether you're writing ASM.js or C or Rust or any language that you want, you can compile it down into this shared AST that then browsers are going to be able to transform into assembly more efficiently than they could native JavaScript. And because Node runs on V8, we get this for free too because Chrome has V8 and they're updating it to run WebAssembly. So that's cool. All right, so I've super glossed over what compilers are and abstract syntax trees and how this all works. I highly recommend Mariko's talk and also blog post about how to be a compiler. She has a really cool demo where you can see code become abstract syntax tree, become something else. And that's what's really underlying all this. So if you're curious about the underlying mechanics of how this all works, go check it out. All right, demo time. Woo, that's not my demo. That's my demo. All right. OK. So what we're going to do here, and this would not pass the linter. I should write a separate lint file specifically for demo code that actually rejects any files that aren't horribly written quickly and late at night. So what's our index.js going to do? We're basically going to take in a WebAssembly file. We're going to load it as a JavaScript module, because in the end, that's what you get in your Node process, is a JavaScript module, just like if you'd done module exports. And then we're going to run its function. And I've written all these demo functions in ASM.js, so we can actually load it in as JavaScript as well, compare the performance. It's very cool, and nobody has to brush up on their C, which I am grateful for. So the way you load this right now, and here's where we get to the please don't do this in production part, is pretty awkward. There are some other functions that exist on the Wasm object that don't actually work. They don't exist at all. They're just stubs. They don't even bother throwing an error because you're not supposed to be using this yet. So at least not in production. So what we're going to do is we're going to read in a file, which is the compiled WebAssembly module. And you can see this little weird file extension here, which I made up myself, but is because there isn't a standard yet, because this is new. And what exactly does a file like this look like? Well, first, let's look at what an add function is. So this is the same function we saw before. We got a module, we use this little useASM string, we declare a function, then we export it. Pretty straightforward. So this gets compiled down into this. This is the WebAssembly abstract syntax tree. You can see here it's using a more Lisp-like structure than the JSON structure we saw earlier, but it's very tree-like, it being an abstract syntax tree. It's very regular, it's easy to parse, all these good things. And if you spent time in the Lisp parentheses mines, these probably looks really comforting to you. Then it becomes this, which is less readable. But you see some strings in here, and the reason this is less readable is we actually take that abstract syntax tree and we compile it down into a binary format that is one-to-one. It's not actually doing anything, it's just making it smaller and easier for the browser to read. And when you work with this stuff this early, you get to actually read these binary files to figure out why stuff isn't working. So this is a WebAssembly module. This is a hex view for those who don't know. You can see this is basically the column, and this is that doesn't actually highlight that way. This is the row. And here we have the string representation. So you can see these first 8 bytes right here say something, and then, well, they say nothing really because it's 0. ASM. So this is a little header that says this is an ASM file. Then a bunch of stuff. And if you look at this right here, it says B. I'm just going to gloss over that right now. This is the version of this file, which is very important because it turns out this is a very quickly moving standard. To run this demo, I actually had to check out a specific git commit from the tool that compiles ASM.js into WebAssembly in order to get it to actually run with Node v7, which runs v8 5.4. Don't run this in production. I'm going to say that about like 6 more times here because I really don't want anyone to, melt down the world because they decided that was a good idea. Maybe. We'll see how tomorrow goes. So we read in this binary file, and then we have this global Wasm, and you're out there when you're having to use this It might be called this, or it might be called that in Node. If you do browser work, you're kind of used to this little dance of which vendor prefix do I put in front of the variable I need. We don't usually have to do this in Node, but we do here. And then we call, finally, this instantiate module function. And this is really the meat of it. So we have to do a little bit of dancing to turn it into a uint8 array buffer, because it won't do that for us. And in the end, we get this nice module that comes back and looks exactly like a JavaScript module. And then horrible, horrible demo code runs it. So let's see what this does. There we go. All right, so we're going to run this with our add function. And I could use a little bit biggerness. Embiggened? Is that appropriately embiggened? All right, cool. So here we're just adding two numbers together. And you can see the WebAssembly time and the JavaScript time. The WebAssembly is sometimes slow. We're just talking noise here. These benchmarks are basically saying if you add two numbers together in a single function, it's the same. And the reason is that cool talk we just saw about JavaScript engines, they do a really good job actually taking JavaScript with all of its weird ambiguities and turning it into efficient assembler code that actually runs on the processor. And for a very simple function like this addition function, they can do that just as well as WebAssembly can. But let's say we want to look at Fibonacci, the darling of CPU benchmarking tests. So for those not familiar, the Fibonacci, the nth Fibonacci number is the sum of the previous two Fibonacci numbers, where 0 and 1 are 0 and 1, I think. I might have been off by 1 in this. It doesn't really matter. The point is, it's a really nasty recursive function when you write it the easy way. If you write it the non-recursive way, it's still really nasty and takes a lot of math. And that's great when you want to prove that something is faster. And so we take this, and here's my fib. So you can see we get a slightly longer abstract syntax tree, which is full of all these little I32s. These I32s are basically getting rid of the loose typing in JavaScript. Loose typing is great when you're writing code and terrible when you're running code. And so one of the things that WebAssembly does is say, you have to tell me exactly what kind of variable these things are, because if we try and do that at runtime, we have to do this crazy stuff we just saw with JavaScript engines doing optimizations if you run your program, your function a certain number of times. We're just going to get rid of all of that. We're saying this code needs to be efficient. You're going to write it a little lower level by telling me what kind of variables you are and various other things. All right, so let's run this. It does not want to render. There we go. Yeah, come on, there we go. This is still faster than the last demo I gave. There we go, cool. So we can see when we do the 24th fib number, we get 3 milliseconds, almost exactly. That's actually a little freaky, but we'll take it. As soon as we go even a couple more, we start seeing a little bit of a separation and even more. And what we see is that the WebAssembly runs about twice as fast. And this is a relatively simple function, so we're not really doing a ton of loose typing. We're not doing crazy stuff with like string data structures. So why is it so much faster? And the answer basically boils down to the event loop. That we have this really cool thing in JavaScript called the event loop that does all sorts of crazy stuff with how functions run. And when you take this and compile it down to straight assembly, you get this much closer to the metal series of functions that don't have to do a lot of this ambiguity about what the function is going to return, how it's going to return. And that's great. If you're running, there's a lot of applications for much faster things like this. If you run React or anything else like that with a shadow DOM, there's a lot of work there in determining whether or not these trees are different. That sort of algorithm of descending and ascending trees and determining if they're different, you can get a lot of speed gains by using something like WebAssembly. Not in production. So that's cool. I mean, it's basically magic. And we love magic. So what are the benefits? Speed is the obvious one, right? If you can take an equivalent piece of JavaScript code, rewrite it into something that compiles to WebAssembly and it runs twice as fast, that's a pretty good win and something you should feel pretty happy about. There's other ones, though. Less npm post install building. If you run npm, you've run into this where you npm install something and then you have to wait a few minutes for it to run a whole compiler step because it's building the native module. That's if you're lucky and you don't end up having to go back and install 6 different C dependencies into your runtime environment. If you're running in Docker, you get to run this fun game where you install the dependencies, do an npm install, uninstall them all in the same step, so you don't run into your Docker container being 6 gigabytes wide of C dependencies. We can get rid of all of that. Not all of it, but we can get rid of a lot of it by simply compiling down to this common shared format that doesn't require compilation and install time. The other really cool part, this is EmpireNode, not EmpireJS, but we all work with browsers. This is running in a browser right now. You can run compiled system languages like C and Rust and other low-level languages in the browser. And that's great because right now, if you have some sort of something that has to run in a low-level language, either because you have a dependency or because it's just not fast enough in JavaScript, you have to basically call out to the server from the browser, have the server do the work, and then return the result back. If it can compile down into WebAssembly, you can just ship that compiled systems code up to the browser to actually run locally for the user. And that's huge. And really, overall, what this is letting us do is pick the right tool for the job. We write a lot of JavaScript. I love full-stack JavaScript. It's amazing that I can write the same language for both the browser and on the server. I don't have to context switch. I can just use the same massive NPM ecosystem that everyone else uses with all these great tools. But sometimes you really might want to use another language. There's a ton of great data science resources in Python. There's lots of really cool, low-level, highly efficient code written in C. Crypto stuff is often written in system languages because it can be much faster. And what this lets us do is rather than either rewrite everything in JavaScript or use these kind of native module hacks, we can compile down from multiple languages into the same shared WAST and run it all once again in the same place without these awkward intermediate steps. So you want to learn more, you want to do more, it's an open spec. Go to github.com, webassembly/design. Like I said, you can find these slides online, or just search WebAssembly design. This should be the first hit, I hope. Otherwise, they need an SEO expert. And you can see the overall, they have the high-level design patterns where they talk about what WebAssembly is, how it's going to work. They also have the low-level specs, so you can see how exactly this one becomes this, right? There's actually a spec that tells you what each of these numbers mean. And so when you're trying to debug your completely bleeding-edge WebAssembly code that you're not running in production, you can go and see, oh no. See, you don't run WebAssembly in production. No, that's all right. We'll just wing it from here. We're basically done. So you can see that what it is these numbers are doing. You can actually see, is my problem in the compile step down to the binary, or is it the binary running in the browser? You can give feedback if you think that WebAssembly should work a different way. You should say that, oh, actually, I think we should be able to specify, string length this way. You can submit a PR. You can add it into the design process, and it'll be considered by the same people. And you can see what's coming up. You can start working with it. And it's really amazing that it's this open, and you can really get into it. That's it. Thanks.